If I want to find the distance from here to here of this line, how am I going to do that? So let's derive the distance formula. We have some arbitrary line looking all nice and squiggly like that. Whoop. I want to get the distance from here to here, the length of the line, right? What am I going to do? Well, as with all things we do in calculus, we're first going to start by taking a teeny little difference. We're going to start understanding it by a change. So if I want to find the distance between this point and that point, I'm going to apply some properties of right angled triangles. So I can get this point's location with this right triangle, x1 and y1, right? And then I can get this point's location with a different right angled triangle, x2 and y2. Now, if I subtract these two triangles, I'm left with this triangle here with delta x and delta y. Writing that out as a formula, right? Because then we get this length here, that distance squared is equal to r delta x squared plus r delta y squared, just Pythagorean identity, right? And we can rewrite that. We can say that distance is the square root of, and remember that change in x is just equal to r x2 minus r x1 squared plus r change in y, r y2 minus r y1 squared. And putting that up here, ta-da! Well, really, that should be delta d. That's how we get our distance. I'm going to replace that with that for now because that's what we're looking at. Now that we have that, we can say that, yeah, a teeny change in d, or actually, we'll start calling it L now. Teeny change in L is equal to the square root of delta x squared plus delta y squared. And if we integrate that, L equals integral of square root of dx squared plus dy squared. And now, this is how we get from here to here. Either we factor out a dx squared, or we factor out a dy squared. So if we factor out that dx squared, then we get dx square root of 1 plus dy over dx squared. And if we do it with dy, we get the exact opposite. So yeah, this length formula, the length of any line, the line integral, comes from our distance formula, which comes from Pythagorean identity triangles. Wowee, that's pretty cool. Let's go back to our surface area integrals again. If I have that function here, f of x, the line, once I calculate that, is that first part of that integration, right? Then it actually becomes pretty simple because, yeah, like I said earlier, we're just sort of multiplying it by that distance around which axis we're rotating it about and doing the rotation. So if we look sort of at that formula again, S equals, and this time, look, we're multiplying around x. So this is how I'd like you to, or this is how I think. So this is how I imagine the rotation and how I keep from mixing it up all the time, because it is very easy to mix up. If I'm going about x, I need to rotate. If I'm rotating about x, then I need to go this way. Well, how do I create those circles? I have to go up. I have to move in a y direction, right? So in our formula, our S equals, if I'm rotating about x, then I know that it's that 2 pi, because that creates the circumferences, y, because I'm going up that y distance. This is the circle that I'm creating, right? I'm cutting straight through the plane like this, and to get those circles that look like that, I need to create this radius, which equals our y value. Cool. So that's that part. And then I can just plug in that DL. That DL is literally, once we evaluate it, just going to become this. So you can write out a little like DL like that. And now this like makes a lot of sense, right? You can see that at each point we have this DL, it's multiplying by its accompanying circle. And that'll give us a little band of area. If we add up all of those, we get our whole surface area. One thing I'd like to mention really quickly too about the surface area integrals is how it can connect to to centers of mass. You might have seen somewhere else or in a different video of mine that volume can equal area times 2 pi y bar. Well, that same guy also says that we can say that the surface area is equal to 2 pi L y bar, right? And again, this requires some finesse, right? Depending on if we're rotating in x, or if we're rotating about the y, right, then we'll need that x, or if we're rotating about the x, then we'll need the y. But pretty interesting. You can sort of see the connection between our centers of mass and getting our surface area out of that. Like meditate on that a little bit. I think it becomes pretty apparent when you think about it for a little bit. If you've got any given shape, right, and you have that y bar, if you're just going from here to here, yeah, you can turn that integration into simple multiplication by saying, okay, well, this is our length stretched out, or this is how I imagine it, right? If this is our length stretched out, it'll be a little bit longer. So this is our length. We're just multiplying it by that. Then this area, or yeah, we're multiplying it by that, right? Our y bar. This area here is the same thing as the surface area generated by rotating this about, right? Once we multiply by 2 pi, that 2 pi does that for us. So yeah, that's another cool connection that I thought is pretty interesting, something to think about, and that might show up later in your classes. All right, thank you. Good luck with your Calculus 2 journey.